Welcome to the online edition of our Code and Tell.
We're 100% online for now.
So grab some snacks, relax, and get ready for another Junior Dev Code and Tell.
If you've got any questions,
head on over to slido.com.
There's a link at the bottom of your screen now.
We'll do a quick Q&A at the end of the presentation with the questions you asked, so please keep them coming.
Coming to you live, here's our first presenter.
Hi, good evening, everyone. My name is Bak. Thank you so much for inviting me here today. I will be giving today's talk on Introduction to Machine Learning on Google Colab. Okay, so this talk is for people who are interested in artificial intelligence and machine learning. You don't have to be in the IT field. You can be of any profession and of any age. But this talk is primarily a fundamental sort of machine learning, so it's a little bit basic for those who have already had prior knowledge. So it's broken down into 4 parts. First, I'll do a quick introduction, then we'll talk about the fundamentals, and we'll go into the actual code, and then at the end, we'll have some Q&A. Oh, sorry. All right, cool. So a little bit about me. So again, my name is Bak, and I've graduated as a pharmacist. I'm still working as a pharmacist part-time. Currently, I'm studying at Swinburne University. That's where I got the opportunity to participate in a research project on third library recommender system using convolutional graph neural network. I'm working full-time at a medical startup doing front-end work, and those are the tools I use. Okay, so just some quick overview of conceptual overview. So artificial intelligence is a concept or feature you want to implement within a system, while machine learning is the actual implementation that gives the system the AI capabilities. Now, you might have heard machine learning being said hand in hand with the term data science. The reason is that without data, your machine learning models or algorithm are pretty useless because you got to actually train it with some data. It is an advancing field because basically every business wants some kind of machine learning to kind of like tailor the user's experience. And the other thing is with the massive computing power that we have these days, it's quite easily to go through all those gigabytes and thousands of gigabytes of data. And the other thing is that we actually have somewhere to store those data, so in those big data warehouses. So just an example of some of the stuff that machine learning can do. So these faces are actually generated by a neural network. So it's being generated on a website called This Person Does Not Exist. So yeah, so all of these faces here are generated by a machine learning algorithm. And another example here is waterfall. So from this crudely drawn drawing, the machine learning algorithm can create a photorealistic photo. Another thing you might have seen on YouTube quite prominently is the swapping of faces of one actor for the other. So here it tracks all the features of the actors, and using a collections of photos of an actor, they basically track those features and superimpose another actor's face on. This is pretty much the same thing, and it's just swapping of some more cages. Okay, so other application of machine learning is in this list. It's not an exhaustive list. I just want to put it there so you guys can have a look at what other things that machine learning algorithm can do. It's really interesting. A lot of it you probably already been in contact with but may not be aware of, like the recommended system, like Google Recommend, object detection in self-driving cars, and competitive gaming. So that's quite an interesting one. All right, so let's talk about the fundamentals of machine learning. So there are 2 types of machine learning problems. The first is regression problems. This is where you predict the value from a continuum, like what is the price of this property. The other one is classification, where you pick a discrete class from a number of classes and assign it to the sample. Like, is this a cat or is it a dog? And the type of machine learning problem can be determined by how the problem is defined. Basically, what that means is some problems, instead of making it a regression problem, such as what is the price of this property? You can ask, is it an expensive house, cheap house, or is it a reasonably priced house? Obviously, you have to make sure that the question that you ask the machine learning algorithm makes sense in make a business sense. All right, so how to do machine learning. So there are 6 steps that I have outlined here. First, you've got to collect the data. Again, without the data, your model is pretty much useless. The next thing is you got to prepare the data. Raw data contains a lot of no values, incomplete, and wrong entries. There's some things that don't make sense. So you got to work out what are those wrong entries and what to do with it. And this can affect how you train the model. And then after that, you want to build a model based on some kind of intuition of the problem. So you want to know the problem kind of intimately, and then you can basically you need a starting point, and from then you can tweak your machine learning model. Then you train the model by feeding in the data or a subset of the data. Once you're happy with the model, you can use it to predict like let's say a smaller subset of your data set, or you can predict with new incoming data. After that, you want to fine tune the model just to make sure that it is as accurate as it can be. So here is just a simple example that we'll use to run through the fundamentals of machine learning more in depth. So what we have here is a table of Australian dollars and New Zealand dollars. It got two columns. The first column is Australian dollars is denoted as X. And the second column is New Zealand dollars denoted Y. Let's say we have this data set, and we want the machine learning model to be able to basically convert the Australian dollar to New Zealand dollars without us explicitly tell it what is the exchange rate. So this is the rate over time. So let's before we explore this data, let's have a look at some terminology. Okay, so now Y is the label, so that is they call the ground truth, is what we're trying to predict. Y prime is the prediction, which is the output of our model. Theta is the weight tensor. It's saying like how much the attributes matter, and the attribute is denoted at X, a lowercase x here, and it is the column in the data set. In our particular data set, we only got one attribute, and that is the Australian dollar. And capital X is the sample, the row in the data set. So in our particular example, there are 10 samples. And B is for bias. Now, you might have heard me use the word model, algorithm, neural network, all interchangeably. At least for the purpose of this talk, they all mean the same thing. Just before, I used the word tensor. Now, this word, when I first encountered it, feels really foreign, and I didn't understand what it means. But really, at least for the purpose of this talk, it's just think of it as a matrix or an array, or even an array of an array when it needs to be. So it's an n-dimensional array. All right, so let's get back to our example problem. All right, so let's look at the Australian dollar. So when you have no Australian dollar, you expect to get no New Zealand dollars. And during a really good Australian economy, you might get may convert $1 Australian dollars to 1.2 New Zealand dollars. And during a really bad economy, $2 Australian dollars may only get you 1.8 New Zealand dollars, and so on and so forth. So we have this data set here. So what we want to do to explore the data set and see if we can develop any intuition, and from the intuition we can build some kind of basic model first, and from there we can progress. All right, so to explore the data, we'll graph it onto a Cartesian plane with the Australian dollars on the horizontal axis down here, and the New Zealand dollars on the vertical axis. Now, looking at the data, we can see that it's almost formed a straight line with a gradient around 1, and the intercept at 0, 0, which is the origin. So let's draw that line. So we'll call it the line of best fit, or really is our hypothesis or intuition. So I will be using the word hypothesis from now on. Okay, so and we look at this. It's pretty good hypothesis. So and we'll probably use that as our basis of our model. And the equation for a straight line or a linear line is the linear equation. The linear equation is denoted here. It's y equal mx plus c. Now, to make sure that everything is consistent in machine learning terminology, we'll just convert some of those over to machine learning symbols. So we got y prime. Again, y prime is the output from our model. Theta, again, that's the weight, basically is saying how much the attributes matter. Now, we got a capital X here. For this particular example, you can see X, capital X, and lowercase x as being the same because we only got one attribute. But if you got millions and millions of attributes, then that changes things a little bit. But for this, for the sake of simplicity, capital X and X is the same. and then we plus b, which is our bias, or in linear equation term, that's the y-intercept. All right, so now we got, okay, we'll go back. So we got y prime, that's what we want to predict. We have the data set which has the values of our x, but we don't know our theta and our bias. So where do we start? We take a guess, and that's what you find in practice is that when you start these when you start training these models, you basically take a guess of these the weights values and the bias value, and this process is called initialization. All right, so let's take a guess. So we have, for this particular example, we got theta as equals 0 and b equals 2. What I draw is this horizontal purple line down here. And then what? Where do we go from here? Firstly, that's not a very good guess, but the important thing is we got somewhere to start, and that is quite an important thing to know. But what do we do from here? Well, we can take another guess. That's not very good either. And we can take another guess. That's not very good either. And another guess. Again, this one is a little bit better, but not where we want to be. And this process can continue on. And you can see that that's not very intelligent. And that's nothing to do with learning. It's all guesswork. And we could be waiting forever until it gets the right one. And again, that's not very cost efficient or intelligent in any way. So what do we do? What we want to do is to tell the machine, the model, where the error, what is the error, how big is the errors, and from that error, how can we move towards having minimizing that error. Okay, so what we do, so we'll connect the dot where y, which is our dots here, to the corresponding points on the purple line. So what we want to do is the error are these red lines, and what we want to do is to get calculate the length of those red lines, add them all together, get an accumulative score, and then we can use that to move on to our next step. So the processing of errors is called the error loss function, and I will refer to it as a loss function from this point onward. For regression problem, a really popular, common loss function is the root mean square error, represented by this equation here. Now, this may look a little bit complex, but it's actually not. So let's just quickly break it down. So part one, start in parentheses. It's got yi minus y prime I squared. So this is finding the square error. What this is actually asking is what is the length of those red lines? What are the lengths of those red lines? And then square it. Okay, to get the lengths of those red lines, first we've got to calculate y prime. Again, that is the output from our model. Just a recap, our model is down here, our hypothesis, our model right down here. So we've got theta times x plus b. So let's start with this particular example. So here's our theta, that's our x, and then this is our b. So you got theta times x plus b, which is 2 times 0 equals 0 plus -3, we get -3. So that's our prediction here. And we do the same for all of the samples in our data set. After that, we'll find the length of those red lines, which is the error or the difference, called Cartesian difference, distance. And so we'll go 0 minus -3 equals +3. So that's what we have here. And we do, again, we do the same thing for all of the samples, all the rows. And then the next thing we do is we square it. So 3 squared is 9, and then all of these squared. And just to make sure that we are correct, -5 squared is 25. Now, why do we have to square it? So 2 important reasons. Firstly, it gets rid of those negative values. Secondly, is make sure that this equation is differentiable, and that's an important point, and we'll get to, I'll explain why that is very important in machine learning. Okay, the next part is we want to get the sum of the square errors. So we got this capital A looking sign here, and that's a sigma symbol. Basically, it's a sum over all of the rows in the data set. So from I, which is the first row, to the last row. So that's what we'll do. Okay, so if we sum all of these values here in the last column, what we get is a value of 103.42. The next part we'll do is to find the mean, the average. So to find the average, we divide it by the number of rows in the data set. This particular data set has 10 rows, so we'll do that. 103 divided by 10 is 10.342. So that's what it is there. And the last part is what we get the root, square root of that value, which is 3.216. And you can see that the name of the function kind of informs us of the process that we need to take. Basically, we have to find the error, then we square the error, then we find the mean of the square error, then we root it. So that's what the answer is there. So what that means is that for this particular pair of theta and bias values, our error score is 3.216. Now, if we do this for all possible theta and bias pair values, what we get is a graph that looks like this one on the left. Okay, so let me explain what this graph is. So this is called a surface plot. So on the bottom, so you got two axis lying on the bottom here. So it's a little bit hard to say, but this particular axis is the theta, so that's our y-intercept, and down here, that's the theta, that's the slope, and then you got the bias, that's the y-intercept. Okay, and we got the vertical axis running up, that's the RMSE value. So if you pick any point here, you could find the if you pick any point here, you could find a corresponding error score. Now, where we want to be on this graph is at the bottom here, this very tip. That's the global minima. So that is where the error score is the smallest it can be. Now, let's move. It's a little bit hard to see from this graph just because it's a little bit zoomed out and the scale is a little bit large. But so what we do is we'll have a look at this graph on the right here. What this is a contour graph. It's basically a top-down projection of our surface plot. Now, contour graph uses contour lines to denote the error scores. So let's pick this particular line here. Again, font's a little bit small, so we won't be able to see it. But where I'm circling, the value is 80. It's saying that all the bias and theta values pair that lies on this line will have a root mean square error of 80. Now, we can use this to kind of visually validate this point here. So if we find the center of this ellipse, and before we go do that, all of these ellipses are concentric. Basically, they share the same center. And if we find the center of this innermost one, or really the center of all of them, this is where the error score is the smallest. And I think it's around here. I didn't draw it up because we can just visually do this. Eyeball it. And if you draw a vertical line straight down from that center point to the intercept, so down here is the intercept. So again, that's the bias. We get to 0. And if you draw a horizontal line across to this axis, that's the theta, you get around 1. It's not at 0. And this visually validate that this point here is where the error score is the smallest, and that's where we want to be. Now, in practice, it's actually not possible to draw those graphs because one is CPU intensive, and the other thing is that again, data set in practice has millions of attributes, and that's not visually possible to produce those kind of visual representations. So what do? Most of the time, what we see is one point on any of those graphs. And what we want to be able to do is that from that one point, find out where we are, what is the slope, so then we can know the direction that we need to go. Conveniently, mathematics have given us the tools to do that. And to be able to go down into that global minima is called gradient descent, or as the name suggests, rolling down the hill. And that's exactly the kind of analogy that a lot of people use when explaining this process. Basically, imagine this is a red ball and you want it to roll down the hill into that lowest point. All right. Now, like I said, mathematics are giving us a way to do this, to calculate the slope at any point on a graph, and that is through differential calculus. All right, so we have to talk about differential calculus a little bit before we go on with the machine learning algorithm. Otherwise, it's going to be very hard. I'm just joking. There won't be any differential calculus in this talk. It's a little bit involved, a little bit more than a 30 minutes talk can give, because you got to look at partial derivatives and all of that. So a little bit of a throw on you. But basically what we want to do is that move from any point on this graph to the bottom here. And to do that, and that's pretty much the fundamentals. And so we'll move on to the next part is actually the coding. All right, so I'm using Google Colab at the moment. So it's an online notebook provided by Google where you can do a lot of things. Recently, I just found out you can actually write HTML, CSS, and JavaScript. That's fantastic. But mainly it's used for Python and machine learning. So we'll be building a simple neural network in Google Colab. So the machine learning library we are going to use is called MXNet. And the first thing we'll do is we'll install it. So MXNet is going to be very quick to install. It's not that much. My internet might be a little bit slow because of everyone using it at home due to the lockdown. All right, so the next thing we want to do is to import the relevant libraries. So there are 5 lines of imports here. The first 2 lines is what we're going to use to actually build our model and actually train it. This third line here is to import the data set that we're going to use, and I'll talk about the data set in a second. The last 2 lines is more utility functions. All right, so let's import that in, and all right, so after we've imported it in, let's have a look at the data set. So the data set is called the Fashion MNIST data set, and what it is, it's I'll get back to this slide. The Fashion MNIST dataset is a collection of 70,000 images of clothing items, 60,000 of which are used for training purposes, and 10,000 images for testing purposes. So this particular dataset is pre-split. So basically, if anyone who used this dataset will have the same images for training and the same images for testing and validation. Each image is 28 by 28 pixels, and they are categorized into 10 different groups. So what the groups are, these ones. So you got t-shirt, trouser, pullover. We'll have a look at what they actually look like visually in a second. Now, if you notice, these are labels that are used for human readability. What actually is in the data set are these numbers here. So it's been encoded. The reason why it's been encoded is that machine learning models work best with numbers. It don't work well with strings or anything. Even images have to be converted into numbers. And images are made up of RGB values, and those values that would get stored. So basically, if you have this classification problem, what you want to do is to make sure you encode your labels into numbers and digits. All right, so let's get back to this slide quickly. So what we do here is we're downloading the data set, and we store it in we're downloading the training data only, and we store it into this variable. And we'll split the variable. We'll explore the variable a little bit. By splitting, we'll get the first sample, and then we'll get the attributes, which is like the RGB values of that particular image, and we'll get the label. So let's use it, a t-shirt, trouser, so on and so forth. And we just have a look. So it is 28 by 28 pixels. All right. Now, even though I said the data set holds those 0, 1, 2 to 9, we still need the text labels for us to understand quickly what those values mean. So we'll store all of those labels into this into this array here. Okay, so that's done for that. So let's actually execute the code, and then we'll move on to the next part. All right, so right now, what we do is to explore the data set. So just have an idea of what we're looking at. So we're using matplotlib to actually have a look at the data. So we're just plotting the images. So let's have a look at the data and see what we come up with. All right, so this is what we see. Again, that's a 28 by 28 pixels image, and got a pullover, an ankle boot, so on and so forth. All right, not the best looking colors. All right, cool. Now, the next thing we want to do, at least with MXNet, is to make sure that the images are in the right shape. So we need to transform it into the tensor. So that's why this transformer is here for. You may not get, you don't get this, you don't need to do this in machine learning libraries like TensorFlow. I believe the data comes to you as ready to go. Okay, so we transform those. And now, again, there's 60,000 samples that we have there, and we can't just dump it all into the model. It might it's very inefficient. So what we do is we'll break it up into little batches of 256 samples per batch. So that's just an arbitrary number that I've kind of selected. Okay, so and then what this data loader does is break that whole 60,000 collection down into batches, and then what we'll do is give the trainer, and we'll talk about the trainer in a second, a batch at a time. All right, so we're just having a look at the batches. So there's after splitting, we get 235 batches altogether. And we'll do the same for the testing set, subset. So that's what, so train equals false. Basically, we're just grabbing this, the other 10,000 samples, and we transform it like what we did before, and then we'll break it up into little batches, and there's 40 batches of 256 images in the testing set. All right, so let's actually execute the code. So, okay, that's done, and now the next thing we will do is we're actually going to build the model. So you can see here that there's really 1, 2, 3, 4, 5, 7 lines of code to actually build a neural network models. Okay, so the first line is we'll initialize a sequential model, and it's an empty model. It got nothing in there, and a sequential model means you'll run the layers sequentially as they are added, and these are the layers that I've added into our model. So we'll call our model net. Now, if you there are 3 layers here. Now, if you ask me why there are 3 layers, I can't really tell you why I chose 3 layers. And if you ask me why there are 120 neurons in the first layer, 84 neurons in the second layer, and 10 neurons in the last layer, I can't explain why for these first 2, but I can tell you why in the last one. Now, let's start with the easy question, is that why are there 10 in the last layers? Now, recall there are 10 different clothing items. In classification problem is that, you in the last layer of your model, you need to have as many neurons as there are classes you want to predict from. All right, so that's the easy question. Now, the harder question is why these 120 and why these 84? There's no good answer for it. In machine learning, it's trial and error. You find the best combinations of number of layers and number of neurons in a layer. If you got too many layers or too many neurons, you risk slowing down the training and the testing time. But if you got too little, then you sacrifice accuracy. So that's why I say it's not a clear cut on what numbers you should put in there. Now you notice this activation function here. So an activation function controls the output of each neuron. ReLU stands for rectified linear unit. What it does is that if the neuron gives out a negative number, the function will clamp it to 0. Basically turn, let's say a -2 trying to come out of the neuron, it'll get clamped to 0. So only 0 and positive numbers from 1 to positive infinity gets output by the neurons. Down here you get net.initialize. Net.initialize is basically pick those random numbers. So as the same as what we did in the previous example. Okay, so we're just having a look at the layers and the weights and the biases inside. You can see that each layer have their own set of weights. So again, that's the theta, and the bias, again, that's the B, and yeah, so a pair for each layer. Okay, so now we have to define the loss function and what we do and the trainer. So in classification problems, a popular one that we use is the softmax cross entropy loss function. It's a mouthful, and I'll explain to you guys how that works in a second. And then we'll get create a trainer here. Basically, we tell the trainer this is what our model looks like, and this is the type of gradient descent that we're going to use. SGD stands for stochastic gradient descent. And recall back to that surface graph that I showed you guys earlier, where I drew that arrow going from the ball down to the bottom. You don't get that nice descent. What you get is this more of a zigzag pattern, and that's a stochastic gradient descent. Now, learning rate, we didn't talk about it at all, just because it's a little bit involved and might lengthen this talk a little bit too much. But learning rate is basically like how much it should move from the ball should move from its original position. If you put the learning rate too big, it might overshoot that lowest point, and then it might just keep doing this kind of like a pendulum kind of motion. But if a learning rate that is too small, then you don't get anywhere anytime quickly, and that's not very ideal either. The kind of optimal learning rate is between 0.001 and 0.1. Hence, we've got 0.1 in there. So let's talk about softmax cross entropy loss. So if you feed in the prediction from the model and the label that from the data set, it will generate the softmax cross entropy loss function will generate an array that looks like this. This is a probability array. And if you graph it, this is what you see. Basically, it's saying there's 91% chance that this particular sample is a t-shirt. And we just define some accuracy metric. Now, I just want to bring your attention to this line of code down here, and it's important. It is relevant to the previous slide. So note how these are in the order that they from 0 to 9. So 0, 1, 2, 3, 4, and this is also the index that will what we need when we use it to find the word labels for human readability. So what it does here is just asking where is the highest value. So where is this? And get me its index. So for this particular example, the index is at 0, and we use that index to retrieve the actual word label. So that's what it's doing right there. All right, so let's actually build our model. So I got to run the code as we go. So that's the softmax cross entropy, our accuracy function. All right, now this time we are up to actually training our model. And I'm going to do this a little bit backwards, a little bit. I'm going to run the code before I do the talk, just because it does take a little bit of time. I'll let you guys see what it's actually doing a little bit, then I'll jump back into this explanation of the code. So it's running the model here, and you should see the output in a second. There we go. So it's already run the first epoch, and it took 8.7 seconds. And I've run this many times, so it's average around 8 to 9 seconds. All right, let's get back to the slide so we can have a look at what each line of code actually mean. All right, let's start from the top. So for epoch in range 20, basically we're saying train this model 20 times, and that's what we're doing. All right, and each time before we start training, each time just set all these values to 0, so then we can have an idea of how the loss, the accuracy of the training time, and the validation accuracy. We'll start the timer here, so then we know how long it takes. Like I said, each epoch takes around 8 to 9 seconds. So this is where the training actually occurs. So what this here with this line with autograph. Let me just run this code. No, that's fine. Okay, so I had syntax highlighting going, but I'm not sure why it's not working. All right, so what we're saying here, so with autograph.record, so remember how I said that the loss function needs to be differentiable, and you have to learn differential calculus. Well, with machine learning libraries, you don't actually have to learn much about differential calculus. I mean, it's good to know, so then you can actually create better models. But what it does here is that it automatically differentiate it for you and find a slope. Basically, it's automatically find a slope, record it, and then it will tell the model how it should move. All right, so this is where we actually put the data in. So output equal net data. So we input our data set into our model, and whatever the output is, we'll store it into this variable. The next thing we'll do is we compare our prediction to the label. So that's what. So this is our loss function here. So here's our prediction. It goes pop into here, and our label from our data set, and then we'll record that the loss values. So loss dot backwards. This is where we tell the model how wrong it is and tell it how to move. All right. So once that's done, we'll grab the next batch and we'll do the same thing. We'll we aggregate all those loss score and accuracy score in here. And then after that, what we do is we just quickly validate our model at that current epoch, at that current iteration, to see how accurate and it is. And then this here just printing out what you see on the screen on the bottom here. All right, hopefully that finished training. All right, fantastic. I don't think you guys can see this, and I can't really zoom in much more, but each epoch took around 8 to 9 seconds, and the accuracy actually got better. So the top one is 0.727, and the last, the training accuracy got up to 0.915. So basically saying our model is 91% confident that it can get the right answer for the clothing items. Okay, so that's all right. The next thing we want to do is just quickly test our model. So what we're doing here is just getting the first 10 samples from our data set, the same data set. Ideally, you want new data, otherwise you kind of risk it kind of remembering what it has the values are. So we're just grabbing the first 10 data rows, and then we'll transform it like we said before. Then we feed it into our model right here, and then we'll get the highest, the index of the highest value, argmax, and then that's our prediction. And then after that, we'll just plot it out using matplotlib again, just to see how good our prediction are and have a visual validation of our model. So let's do that. So we'll run the test, and then we'll output our predictions. All right, so what we have here, the first example, it is a t-shirt, and our model predicted to be a t-shirt, a trouser, good, very good. Pullover. This one it got wrong. Every time I run this model, I'd always get the dress and the coat and the t-shirt and pullover a little bit wrong, just because they do look a little bit similar. So here, it's a dress, but it thinks it's a coat. Well, this is a label, but it thinks it's a shirt. This is a bag. Again, this is a shirt, so this one's correct. Sandals, t-shirt. Yeah, and that's pretty much the journey for that's how you do machine learning. And before I leave you guys and move on to Q&A, I just want to leave you guys with some resources. And my recommendation, as they are listed, I would recommend you go firstly start with this course here by Andrew NG. It's a Coursera course. It's free, and it runs through the fundamental much more in depth than what I have here, obviously, because I only got 30 minutes and he got a few lectures to go through and to run all the stuff through. Next thing you want to do is just pop over to Google and have a look at this machine learning crafts course. It's a little bit more interactive, and it's actually really fun to play with. Sometimes you're forgetting what you're there to actually learn. Next thing is you want to look at the Washington University by Professor Jeff Heaton. He does a lot of different type of machine learning models. You do object detections and generate faces like the one that we saw earlier in the presentation. And that is pretty much. Thank you so much for listening, and I'll welcome any Q&A that anyone may have. All right, sorry guys. Cool. Do you have to learn Python to work AI machine learning, if not any good resource for JavaScript devs. So Python is kind of like the de facto language for machine learning, but there are TensorFlow JS. So basically, it's a JS library for machine learning. It's not the most powerful, just because it's basically you kind of tell the user's browser to do all the work. And like I said, you need the massive computing power of the backend server to actually do that. But have a look at TensorFlow JS. There's a lot of interesting stuff you can do with it, and there's a lot of tutorials too. What areas of math should I study to get into AI ML? Learn your basic mathematics first, but like I said, differential calculus, probability, because really it's a lot of to do with probability. So I would do that. So really no, but yet matrices, that's another thing that you want to get to know quite well, because to like I said, like the machine learning libraries does a lot of the heavy lifting for you, but to understand it and creating new models, you really got to know your matrices, differential calculus, and derivatives, and all of that. Are there many courses at uni that offer machine learning? Not at Swinburne. The reason why I got into it is again through that research project that I participated in. But from at Swinburne, there was not much on machine learning. But but as you move on, I'm pretty sure there will be other courses. There are courses that overseas university, like I think Princeton, so that's the American university, they offer these data. They call it data science, and it's pretty much almost the same. What is the minimum level of math knowledge do I need to know to get into ML? Like I said, you want to get at least finish year 12 mathematics. Is it possible to detect deepfakes? So there are deepfakes, machine learning models to detect deepfakes. So yes, there are. Have you used things like TensorFlow or Core ML? Thoughts on them? Yes, I have used TensorFlow. I haven't used Core ML before. TensorFlow is actually quite good. It's a little bit, it's a higher level of abstraction, especially now you got Keras is an extra level of abstraction on top. It makes creating machine learning models quite good. And you can actually run TensorFlow on Google Colab, actually. It's just that for my project, I use MXNet, so I kind of like use that here for the presentation. Is there an alternative to Google Colab that I can download? Yeah, you can get, what is it called? Python notebook. I can't remember what it's called, but basically Google Colab is just an online version of that. I might have to get back to you on that one. My memory is not serving me right now. Yeah, what do you think of Jupyter Notebook and Google Colab? Yeah, that's the one, Jupyter Notebook. Thank you, Anonymous. Yeah, Jupyter Notebook is pretty much like Google Colab. Google Colab have extra functions, like so how I'm presenting to you guys is through what the Google call magic functions. Basically, I put 2% signify to HTML, and I can start writing HTML onto Google Colab, and actually HTML, CSS, JavaScript. So yeah, that's fine. Use that, no problem. How could you improve your example to ensure there are less false positive for the clothing? Like I said, you can run it for more epochs. You can have more layers, and you can use different kind of algorithm. One I show you guys is very simple. The model I show you guys is multi-layer perceptron. It's very, very simple. There's better models out there that you can actually just download and implement, play with. And I encourage you guys to do that. It's actually a lot of fun when you do it. And yeah, there's a lot of tutorials online that you can have a look at. But yes, yes, that is pretty. Oh, and another thing you could do is I didn't really talk about normalization. So normalization is important. So like I said, RGP value is between 0 and 255. What you want to do is to clamp that down to -1 and 1. Normalize that, then that process is normalization. Normalization makes it better, makes it more efficient, and makes it more accurate. And that is the last question. Thank you so much for listening in. I'll hand it back to the guys at Junior Dev.
thanks for tuning in to Junior Dev Live.
And you can stay up to date on everything Junior Dev on Twitter or on meetup.com.
From the rest of the team, stay safe and enjoy the rest of your week.
Bye!